Okay, this is Intro to Heap. It's one of the spookier topics in binary exploitation, but hopefully it shouldn't be very spooky during this talk. So we'll start by kind of going through what a heap is and like how the heap is designed, and then we'll go into the actual like using it to exploit stuff. But understanding what the heap is and like how it works is pretty key to understanding all the exploits. So we'll go pretty far in depth on that first. Okay, so what exactly is a heap and what does it do, right? When we're writing C code, we want some way that we can ask for kind of memory that's not going to go away after our function has finished executing. And really what we want is we just want like some API that we can ask, hey, give me n bytes of memory, and then it will give us back a pointer to n bytes of memory. Um, and then we can use that however we want. And then when we're finally done with that memory, we just give it back. So that's essentially the API that we want. And the question is, how do we implement this? And it turns out to be harder than you may expect. So um, one of the main problems with this is that the like a program can only request entire pages from the operating system. So if your program needs more memory, it can only request memory in big chunks of 4096 bytes, which usually we're not going to want big chunks of 4096 bytes. We may want like 20 bytes or something like that. So uh, really what we want to do is take these big chunks and break them up into smaller chunks and then have some code that manages these smaller chunks for us so that we don't have to deal with uh, making sure that we don't allocate the same memory twice or something like that. So we essentially just want like a program that's going to solve all these problems for us that we don't have to worry about. And that's what the heap does. So the way that the heap works kind of under the hood is it starts off by requesting a really big chunk called the top chunk or the wilderness chunk. And this is just like a massive contiguous region of memory that the heap has allocated. And when we ask it for smaller regions, so say I ask for 50 bytes from the heap, what it's going to do is it's going to split the wilderness chunk into a a little region of 50 bytes and a big region that's like the rest of the wilderness chunk. And then it's just going to hand those 50 bytes to us. So um, like subsequent calls to the malloc, which is the like allocation API call, will just like break off a piece of the wilderness chunk and hand it to us. And um, there's this a struct in libc called the heap main arena, which kind of keeps track of all of the high level heap metadata, which the main arena keeps track of like where the wilderness chunk lives and some other stuff that we'll talk about later. But the arena is not terribly important in this talk. Okay, so I just said that the arena isn't terribly important, but here I have a picture describing what it looks like. So um, the main arena is just the struct. It has like some pointers in it to various like heap metadata things, and the important thing in this picture is that there's just a pointer to the top chunk of the main arena. So when you want to break off memory, it just looks up this pointer in the main arena struct, breaks off some memory there, and hands it um, back to like the user program. Okay, so um, that's allocation. Allocation kind of makes sense, right? When we just like cut some memory off, the top chunk shrinks, and then we give that memory back. So um, where it gets kind of complicated is when we talk about I guess this is another picture of allocation. I don't know why I have so many pictures of this, but yeah, this is what it looks like. If you were to allocate two chunks, you get like chunk A, chunk B, and then you have the top chunk down here, which is like really big. So it's just splitting the chunks kind of sequentially, as you might expect. Um, so where it gets complicated is when we want to give the memory back, right? So say we've allocated 50 bytes, and we've finished using these 50 bytes that we were using. We want to give it back to the heap so that the heap can reuse this memory. Um, and uh, this is where it gets kind of hard, right? Because what we really want to do is kind of reattach the memory to the top chunk. But we can't do this in most cases unless the chunk that we're freeing is like right next to the top chunk in memory. Like they're literally touching, and then we can just make them into one big chunk. If they're like disjoint in memory, we can't recombine them, so we have to do something like more interesting in order to put them together. So here's a case where like we can't recombine the top chunk and the chunk that we're freeing, right? So if we have like chunk A that we're freeing and there's chunk B in between them, we can't put chunk A back onto the top chunk because chunk B is in the way. If we were to free chunk B, then we could like combine them all back into one chunk, but until we free chunk B, we can't do that. So instead, what we're going to do is we're going to take the free chunk and put it in a list of free chunks. And then when we allocate later, we'll just look through this list and see if there's any suitably sized chunks um, that we can give to the user. And if there is no such suitably sized chunk, then we will take it from the top chunk. Um, Now, if you're actually writing like a user program, right, you would want this like free list lookup code to be extremely fast, right? You don't want your code to be stuck in libc looking for like free memory in in the free list the whole time. So the malloc like heap designers have really like gone out of their way to make this efficient, and a lot of this efficiency is what we're going to be exploiting. Okay, so this is kind of what I was describing in the last thing, where it's like you have a list of free chunks, and in this implementation the chunks have like no restriction on what size they are. You just put all the free chunks in a list, right? And the issue here is that if I'm looking for a chunk of size 0x100, I'm going to have to look through like all the chunks until I find one that is bigger than 0x100, right? So um, this is going to be really slow because, like, worst case, I have to look through the entire free list uh, to allocate my chunk. Like, I may look through the entire free list, determine there was no free chunk of this size, and then just allocate from the top chunk anyway. So I just wasted a bunch of time. So this is not efficient enough. We need to come up with a much more efficient way to do heap allocations. So the main idea that we use is we bucket the chunks by their size. So for every size chunk, there is a separate free list, and these free lists are called bins. So every size chunk goes in a different bin, um, and uh, the idea is like um, if the bins are kind of done by size, in order to find a chunk of a specific size, we only have to look through the bin of that size, um, and then we greatly reduce the number of free chunks we have to look through because we're only looking through like the portion that are probably the right size. Um, and in fact, there are some bins called fast bins in the heap, which are for really small chunks, so size like 0x10 to 0xb0. Um, and this is essentially like the idea is that allocations of small size are made very frequently. So we want the like free list lookup code to be really simple and really fast. And because it's really simple and really fast, it's easy to exploit for CTFs because the code is pretty simple. Um, yeah, a fast bin, right? As I was talking about on the previous slide, it's just a singly linked list of free chunks that are all of the same size. Um, So when you allocate for a small chunk size, what it's going to do is just let's say I'm trying to allocate a chunk of size like 25, right? It's going to round that up to the nearest small chunk size, which would be uh, 32 bytes, because it's a multiple of 8. So 32 bytes. Um, and then we just go to the fast bin for things that are size 32 bytes and just find the first thing in the fast bin, because that element is free. So we just pull that element out, and now we have somewhere to put our 25 bytes. So here's what this fast bin looks like. So we have essentially just a linked list of free chunks, all of the same size, right? So when we allocate something of size 0x80, we're just going to pull free chunk A because like it's unallocated memory and it's of the right size. And then we just kind of shift the linked list over one. And then if we allocate again, we'll get free chunk B. Um, okay, and so I guess also we should say, if we were to free some other chunk, let's call it chunk D, we would put free chunk D in front of free chunk A. So it kind of gets pushed onto the front. And then if we were to allocate again, we would get free chunk D, and then we get free chunk A, free chunk B, and free chunk C. And then if we completely exhaust the fast bin, we'll start pulling stuff off of the top chunk again. Okay, so yeah, the idea is that every chunk in the list is the same size, so we don't have to do this really slow search. We can just take the head of the list. Um, there are other bin types in the heap. I'll talk about one later, but they're not really important. They come up in a lot of more complicated attacks, but we probably won't talk about those attacks today. Um, it it the only real difference is that the other bins are doubly linked and circular. So instead of just being a singly linked list like the fast bins, there's like a backward pointer too that points backwards, and it's also like a circular list. Um, but yeah, that won't really be important until the end of the talk, and we'll talk about it later again. Okay, so that's the kind of basic idea of a heap in general. We'll talk quickly about the specifics of how the glibc heap is implemented, because that's probably what you would be exploiting in a CTF. So first of all, the in glibc, when we have these the free list, the pointer, the linked list pointer is called FD for forward. Um, and the backward pointer, if there is one, is called BK for backward. Um, so there's those two things to be aware of, and then there's also the fact that every chunk is allocated with an additional 8 bytes preceding it, specifying the size. So here's a picture of like a free chunk and an allocated chunk. So when we have an allocated chunk, we just have a chunk with a bunch of user data, and the pointer points to the start of the user data, and then 8 bytes. The 8 bytes before the user data, there's like a little size attached to it. So um, essentially, when you allocate like say 20 bytes, you actually get 28 bytes. because you're getting this size thing that you're unable to use when you're actually writing user data into it. And then the idea is that when you free a chunk, instead of keeping track of the linked list somewhere else, you just turn the chunk into a linked list node. So when a chunk is free, instead of having user data in it, it has all of the like chunk metadata in it, like the forward pointer and backward pointer, and like the size of the next chunk and the size of the previous chunk, um, and a bunch of other stuff like this. But we only really care about the forward pointer in this talk. So remember, this is just the in the free list, the forward pointer just points to the next free chunk. Um, Okay, so we'll now talk about kind of how these attacks are going to work. So there's generally two methods um, of doing like a heap exploit. One is kind of trying to get overlapping allocations. So we try to cause the heap to allocate two structs at the same underlying memory. Um, So we may allocate like an object and a string at the same memory, and when we write to the string, it's going to mess up the object, and vice versa. If we write to the object, it's going to mess with the string. So once we have kind of overlapping allocations of two different structs, we can do several things to um, get control of the return of the instruction pointer. Um, but the general idea is we're either going to overwrite a function pointer in the struct by say writing to a string, and there's an object that has a function pointer in it, and then we can call that function, and we will then have control over the instruction pointer, or we just do something more interesting and um, cause a Stack Overflow by like corrupting the object in a really creative way. So maybe there's like a maybe our struct is a string with a length on it or something like that, and we're able to overwrite the length field in this struct. Then we're able to cause like a stack buffer overflow, and we just have to exploit things normally. Okay, so this is kind of what this picture looks like. We have like an object here on the left and a string here on the right, and they have the exact same underlying memory. So if we were to write into the string, we're going to like overwrite the objects like vtable and the objects members, um, and generally just cause really bad things to happen in the program. We won't really focus on what you do at this point. We'll more focus on how to actually get this overlapping allocation in the first place. Because once you have the overlapping allocation, it kind of just reduces to normal binary exploitation. Okay, and the other idea is uh, instead of doing overlapping allocations, we just try to um, get the heap to allocate memory that's outside of the heap. So, for example, we get the heap to allocate like stack memory, and we can overwrite the return address by just writing into the chunk that it gives us. Or we try to get the heap to allocate us like global offset table memory as our allocation, and then when we write into our struct, we'll be overwriting global offset table entries. Um, so these are the kind of two main ideas: is um, having like overlapping allocations and having uh, like arbitrary forged chunks at attacker controlled addresses. Okay, so now we actually get into some specific attacks. So the first one that we'll talk about is a use after free. Um, so this is kind of the simplest heap exploit. Um, and we'll first talk about using a use after free to get overlapping allocations. So the idea of a use after free is that we're allowed to read or write to an allocation after it's already been freed. So we have some object in memory, we free it, and then we continue doing things to that object as if it's still valid memory. Um, and the idea here is that um, the next time we call malloc with this specific chunk size, we're going to get this memory that we've just freed. So we kind of get an overlapping allocation for free, um, just by like we have this chunk that has like is being used as if it's valid memory, although it's already been freed, and this chunk is also in the free list. So when we allocate next a chunk of size 0x80, we're going to um, get back the same chunk. So we have like UAF chunk A, and then we have allocated chunk A, and they have the same memory. So now if we do something to the UAF chunk A, um, it does the same thing to the allocated chunk A and vice versa. So this is the same thing, like say allocated chunk A is a string and UAF chunk A is an object. We can mess with the object by writing to the string. Okay, so that's kind of the idea of like the overlapping allocation UAF. It's kind of just for free, just by allocating again. So how do we forage a chunk into like an arbitrary memory address? So notice that by writing to the free chunk, we can mess with the linked list pointers. So uh, if we have our UAF chunk on the left here, and we're able to write into this chunk as if it's still a valid allocation, when we write to the first 8 bytes of this chunk, we're actually going to overwrite the forward pointer. Um, so this is also going to overwrite the forward pointer for the chunk in the free list because they are the same memory, right? Um, so the idea is that when we overwrite this forward pointer, um, it's actually kind of saying, hey, there's in the free list, I'm pointing to some random memory address that's attacker controlled. So let's say we have like a free chunk, and then we have our chunk that's our malicious chunk, and the malicious chunk is kind of um, I guess it's the one that has the same memory as the UAF chunk, and then we've overwritten the forward pointer of this malicious chunk. Um, so now the heap is going to think that there's another element in the free list, and it's just off wherever we tell it. So um, we could overwrite the forward pointer with like a global offset table address, and now when we allocate the forged chunk, we will get a global offset table address, which is really bad. So yeah, uh, um, after allocating so the idea is that we will allocate this free chunk A, we'll get that memory. We'll allocate this malicious chunk, and we'll get that memory, and then we allocate again and we get the forged chunk that's like not in the heap. So we end up allocating memory that's at an arbitrary address, and then we can use this to write to an arbitrary address. So yeah, then we can just use this chunk to overwrite arbitrary memory like the global offset table or the return address, um, or whatever target you want really. Um, so here's a specific example. We would just overwrite this forward pointer with a global offset table address, um, and then this forged chunk will be in the global offset table. So when we write to it, we'll be overwriting global offset table entries. Okay, so um, in practice, this doesn't quite work because malloc checks to make sure that uh, the size member that's before the chunk matches the bin size that we're allocating. So if we're doing this exploit um, on the 0x80 fast bin, we would expect the heap expects this size argument up here to be 0x80. So if we were to uh, point this, if the forged chunk points to something where the 8 bytes preceding it are not 0x80, the program is going to stop running and say like, hey, you have a heap error. Um, so we need to the way that we get around this is we write 0x80 somewhere in memory, and then we just point to 8 bytes past that. Um, and then when we allocate the forged chunk, everything works out and the heap says it's fine. Okay, so now we talk about double frees. Double frees are pretty similar to a use after free. It's just a little bit more complicated. So the idea of a double free is we're allowed to write to already allocated chunks, and we're able to free a pointer twice. So as you may notice from the name double free, we are freeing something twice. Okay, so um, the idea here is that if you free some chunk A twice, then you get this chunk A twice in the free list, right? And if you think about it, this is creating um, a cycle in this linked list, because free chunk A points to free chunk A, which points to free chunk A, which points to free chunk A, and so on. So if we were to keep allocating, we would just get free chunk A over and over and over again. So this kind of just gives us the overlapping allocations for free, right? Because if we just allocate twice, we get the same exact memory, and if we allocate however many times we want, we still get the same exact memory. So yeah, if we allocate a chunk of size 0x80, we just get chunk A, um, and then if we were to uh, what is this slide saying? This slide doesn't seem correct. Uh, we allocate a chunk of size 0x80, we get free chunk A. That's correct. Yeah, the head of the list just stays free chunk A because this is a cyclic list, right? Um, so if we allocate again, we just get chunk A again. And yeah, this is enough for an overlapping allocation, because we just, every time we allocate something of size 0x80, we get chunk A from now on. Okay, so now we do the forged chunk case, and this kind of just reduces to the UAF. So um, if we have this like cyclic thing, when we allocate something of size 0x80, we get chunk A, and chunk A is still in the free list. So when we overwrite the forward pointer of the allocated chunk, or I guess when we overwrite the first 8 bytes of the allocated chunk, we're overwriting forward pointer of the free chunk. Um, so this messes with the free list again, and we can just forge a chunk again. Okay, so again, in practice, this has some issues. So the heap has checks to make sure that you're not freeing the head of the free list. So essentially, the heap tries to make sure that you're not making this cyclic list with one element. Um, and in order to get around this, we just have to add an additional chunk in between, because it only checks whether the head is the same as the thing you're currently freeing. It doesn't actually check to make sure you're not introducing any cycle. So if we just put in a cycle of 2 chunks, then it works. So if we free A, we free B, and we free A again, we get A points to B, points to A, points to B, points to A, and so on. So there's still a cycle. It's just length 2 now, and the exploit works the same way. Um, it's just we can't do it with only one node, because the heap will notice and crash the program. Okay, so I've said a lot of things, and I feel like I should mention at this point that these heap exploits are very dependent on which libc version you're using. So depending on exactly which version you're using, you may have varying difficulty trying to get these attacks to work. So, for example, this check right here was introduced in some libc version, and if you're using a libc version before that, you don't have to deal with this. And in later libc versions, there's more and more checks. So, depending on the libc version that you're trying to attack, you have to get around more and more uh, complicated checks. Um, I won't really touch on exactly which libc versions things work on. You'll probably just have to kind of figure that out yourself. Usually, you can just read the libc source code. The malloc source code in particular is not super complicated, so it's definitely understandable if you know like basic C. Okay, so uh, we've kind of touched on the two main exploit types. The use after free and double free generally work on all libc versions. Um, and now we're going to talk about kind of more advanced tactics. So use after free and double free are generally the most basic heap exploits. Uh, and you will see them everywhere. Some of the advanced tactics kind of get really spooky, and I'm only really going to talk about one because I think it's particularly useful. Okay, so remember I said at the very beginning of the talk that when we're doing allocations and frees that are larger than fast bin size, so 0x C0 and bigger, um, the free list is instead doubly linked and circular. So instead of just being the singly linked thing, it's doubly linked and it's circular. Um, and the idea here is that we are able to leak heap address, or this says leak heap addresses. This should be leak libc addresses. So we're able to leak addresses of libc by doing this, and that doesn't sound correct, right? Because we're only really dealing with stuff in the heap. Um, but this works because uh, the heap has to keep track of where the free list is. So the head of the free list is actually in libc itself. So there's a fake chunk in libc so that the heap can kind of keep track of where the free list lives. So this is kind of what this looks like. So there's this gray chunk that's like not a real chunk that lives somewhere in libc in the main arena struct. And when we have things in the free list, the forward pointer of this like fake chunk just points to the next thing in the free list, and the like backwards pointers are set up in such a way that the linked list like makes sense and is circular. So if there's only one chunk in there like this, notice that if we were to print the forward pointer, it would sorry, print the forward pointer of the free chunk, we would be printing a libc address because the heap arena bin head here is in libc. So um, this gives us a really easy way to leak libc addresses um, just using the heap, which sounds super spooky. Um, yeah, so printing the forward or backward pointer of a free chunk um, that's like this size and points to the right place is going to leak a libc address to us. And this address is going to be like some address offset in the main arena struct, which is you can just find the main arena struct in a libc. Like there's a symbol for it, and you can just look it up. Cool. Okay, that's the end of the talk. I'll open it for questions now. I realize that this talk may be a bit confusing, just because the topic material is kind of hard to wrap your head around. So, um, yeah, if anybody has questions.